Good. All right, so this week, what's due? Everything. And when you say everything, you mean a project and one or two quizzes, yes?
Yes.
I mean, should you want to do them? I also have an in-class quiz for us to do. I think we'll get to it today. I think we will. We'll see how today goes. I think we will. So an in-class quiz, an in-class quiz is count towards your quiz total. I know we haven't done one in a while. It's been a couple weeks since we did an in-class quiz. I've got a few more planned for us. I just got out of the loop of making them. So I've got a fun one that involves pulling cards today. I've got one for next week, I think. Oh, we don't have class on Monday, right?
Yeah.
Right. But I do have an in-class quiz, at least one more planned for us. I think we'll have two more. The one today / maybe early Wednesday, and then one for next week / maybe early week 10. We're getting there. My God, week 8. We're getting there. Almost done. Yes, survivors. Still coming back for more abuse. Good for you. Good for you. Good for you. Gotta love that what? You watch it, Missy. So let's do a quick recap and then a quick synopsis of where we're headed, or where we're just wrapping. Let me start that sentence again. Let's wrap up what we've done in the past couple weeks, because I have something I want to tag on the end, and I think an example will tag it on well. But I want to look at all the kinds of modeling we've done and where that's taken us so far. When you get to your exam, I posted your exam. It's not due for 3 weeks. It's not due until week 11. But some of that stuff, when you open it up and crack it open and look at it, you're going to be like, I don't know how to do this. That's okay. Some of the stuff you won't know how to do yet. Some of the stuff you can't do yet at this moment. By the end of next week, you'll be fine with it. But right now, it might totally freak you out. That's okay. But there is some stuff you can do, like the Usain Bolt question. There's a question about Usain Bolt's world record time in 2009 in the 100 meters. Okay? And that involves lots of different kinds of modeling, trying to find a curve or a model that fits his data. So I want to do a real quick recap, if you want to start on that exam right now, of the types of modeling we've looked at. What was the very first type we looked at? Do you remember?
Linear.
Yeah, exactly! That was the first kind we looked at. We looked at linear modeling. What was the characteristic of linear modeling? What made you think, let's try to fit that with a line? What did the data look like? Oh, Matt, go ahead. Use the scatter plot. Beautiful. Beautiful. Now I'm going to make this linear data go positively correlated, which means as x gets bigger, y gets bigger. You could easily go as x gets bigger, y gets smaller. But the ones we looked at, for the most part, I think anyway, they look kind of like this. Ish like that. There's like kind of, maybe sort of. And it's noisy. It's not perfect data. It's noisy. It's noisy. But the idea is as x increases in this data, y also increases. But lots of data has x increase and y increase. Do you remember what the underlying pattern with linear model data was? What made it linear versus like quadratic or exponential or any other kind of modeling?
Directions.
Well, kind of. Give me more. I love that, Random, but give me more than just direction. Because, I mean, x gets bigger, y gets bigger. I mean, quadratics do that too, as do exponentials sometimes.
How about the data stays constant?
Boom! Now, I'm looking for consistency, right? Some kind of a consistency. And the general consistency is there's a constant what?
Slope.
Good! Rise over run, slope. There's a constant slope. So that's kind of the hint on linear data, is you have this constant rate of change or a constant slope. Very nice. So when you fit the model through it, I don't know what color I haven't used yet. There we go, red. Something like that. That trends pretty well. I'm going to have you fit a linear model to Usain and see how it fits. But the idea, and it's not perfect. It's not perfect. Those of you going down a 243 road will play with that together, and we'll see how things that aren't perfectly linear can be explained. Otherwise, we'll also explain what linear enough means, right? The data is never perfect. Never. If it is, you question it. That's why Harrison Ford was running The Fugitive, because the data was too perfect. If it's too perfect, you have to question its authenticity. Data should have noise. It's funny, I just read an article on how it looks like a lot of publications get published with doctored data. And this one study went back and looked at 5 replicated studies, all of which showed almost the exact same results. And that aroused suspicion, because a study usually reports on surprising results. Surprising results would be atypical, like running 16 victories in 15 minutes. Like, holy crap! I heard Axel and Kevin ran 14 and 15 though this past time around. That's what I was told. That's surprising, right? That's surprising. But if it happened again next term, and then it happened again the term after that, and then the term after that, and then the term after that, it ceases to be surprising anymore, right? It sounds like that's the norm versus being surprising, and that's what these studies are talking about. So how do you measure surprising? That's what 243 and 244 are all about, those of you making that journey. How should you measure whether something is significantly different? How should you decide whether a drug works or doesn't work? Or whether a drug has a side effect or doesn't have a side effect? All this is what 243 and 244 gets into, and that and a whole lot more. But linear, when it looks linear-ish, when it has a pseudo-constant rise and run, good to go. I'll have you mess with that with Usain Bolt data in your last exam. What was the next kind of modeling we did? Actually, that's fine. You can still see it. Quadratic. We took the bike outside. Let me go down the hill. And we had quadratic modeling as well. Good. Quadratic modeling. Okay. If you had to use one word to describe what that data looked like, what would you use? Say that again. Good. Very good. Parabolic data. I don't know where that voice came from. Somewhere over there. I like it. Parabolic data. Yes, good. So something along this line, or this curve, I should say, ish. Is there a constant slope for quadratic data, like there was for linear? Was there a constant slope? No. You remember what was constant in quadratic data? Nice! The second differences were constant, not the first differences. In linear data, the first differences were constant. In quadratic data, the second differences, you don't have to memorize that. That's just, that is what governs the quadratic data. The second differences are constant. That's the kind of thing that if that ever pops up, it'll probably pop up in your kid's homework more than it pops up like driving down the road in your car. That wasn't the point of the quadratic data. The point was that's why we used that equation to model our data, was because, well actually, what was quadratic about me rolling my bike down the hill? What made it quadratic? Do you remember? Increased speed, which was constant acceleration due to gravity. Due to gravity. That was what made it constant. So it was kind of I cheated a little bit. I knew it was going to happen. So, and that guy is going to look something along these lines here. Beautiful, beautiful, very nice, very nice. So those were the two polynomial models we looked at. I'll have you try to do a quadratic on Usain as well, because as you think about a sprinter in the Olympics, when they leave the blocks, what do? Good, very good. Whether it's the gun or some other part of their body, good. And then what happens as they run? Taylor, go ahead.
They do that.
Oh, they do I'm sorry, they do this. I thought you were raising your hand to say
They
something.
get like, you know, like when you're on the bike and you're like this, and then they go like this.
Oh, so they're using everything in their efficiency to, because at that level, every little advantage helps. Like the shark skin suits on the swimmers and the new techniques on the swimmers. It's amazing. One of the things we analyzed in 243 is Mark Spitz, who won 7 gold medals in the '72 Olympics, and Michael Phelps, who won 8 gold medals in the 2008 Olympics, I think. Maybe it was 04, I don't really remember. But we compare those two. And what's amazing is the slowest time in Phelps's gold medal heat would have beat Mark Spitz in 1972 by a wide margin. But that's because of all those little tiny advantages that added up. So whether it's leaning down, whether it's running. In the 100-meter sprinters, it's just the fact that they have legs that are as big around as my entire body, right?
Okay.
So what do those runners do as soon as they leave the blocks? They accelerate, correct? They accelerate. So I'm going to have you try to fit this model to Usain and see how it fits. Okay, and we're going to figure out how fast he was going at the fastest in there. It's pretty ridiculous, actually. Good. Good. So you'll try that model too. You'll also try some other models that we haven't messed with a whole lot in class, but since you're using Excel in that problem, it's so easy to click through and just try different models. Let's try this one. Let's try that one. Let's try this one, and I'll guide you through it. I'll guide you through it. I have a little YouTube video to show you how to add them all. So good. But while we were doing the bike model, a couple of you other guys suggested another one, didn't you? Yeah, you did. Say no. I remember it happening. I was looking impressed, actually, when it came up. What was the other model you guys proposed?
Exponential.
That's what we spent the past couple of days in, was the exponential model. And the quizzes I have up for this week, I gotta remember. Is it the financial one this week?
Yeah.
Financial and chickens?
Yeah.
Yes, it's amazing how much this model permeates into your lives. And also permeates into where we're going in the last 3 weeks we have together, with the idea of probability. That whole idea of a rate, So the exponential model is this guy here, exponential. Yeah, the exponential model. It looks kind of parabolic, doesn't it? It kind of does. I mean, if you actually look at the data itself and you don't look at it very carefully, you might confuse the two. And you could very easily fit, probably, quadratic models to exponential data or exponential models to quadratic data, because they're both curved, right? They both curve. But what are the differences between exponential data and quadratic data? What are the big differences? Give me as many or as few, well, give me at least one. I should say as many or as few. As few, we just sit there. What do you think, Taryn? Give me one difference.
I was going to say you find like percent with that.
Yes. So linear had a constant first difference. Quadratics had a constant second difference. These guys don't have constant differences, they have constant percentage change. So it makes it exponential. This is constant percentage change. Now that's why it's called an exponential. Exponential is repeated application of a percent, as opposed to repeated addition or subtraction of a constant. So you're constantly multiplying. In class we did coin flips, and we did card pools. I think we did something else too. Rock, paper, scissors. Each of those had a constant multiplier. Whether it was a half, or 25%, or 2/3, each successive number was a fraction of the one before it. Now, the ones we did in class were actually exponential decay, going like this. You could also have exponential growth going like this. That would be the United States population had a 1%, I think, or 1.5% average growth rate per year. 1.5% per year. So the idea is, yeah, it kind of looks like quadratic data, but it's at a constant percentage applied. Okay, because of that, what's another difference that this curve has compared to the quadratic curve?
It's an asymptote, but will never
Oh! Oh, good! What's this getting close to down here? It's getting close to 0, so we're going to hit it. Can't, can it? Can't. What's it also never going to do? Well, go, end. I like that. Whoever said that, I like that very much. It's never going to end. Very nice, Faith, yes. It's also never going to go back up. That's kind of a nice way of deciding whether it was quadratic or not. It can't go back up. That's what a parabola does, yes? Parabola goes back up. Now, I'm oversimplifying this. What a lot of folks do, and I say a lot of folks, an example that pops to their mind is when you see cars, how cars are put together aesthetically, when they actually design the curves on cars, they do what's called polynomial splicing of these models. So they'll say like, the Corvette Stingray. Think of like one of those late 70s, early 80s Corvette Stingrays with the big curvy fenders and whatnot. Those curves are governed by mathematical equations, and they glue them together. So in other words, this curve might be like cubic, and then it might want to go into a parabolic curve that changes a little bit. What they do is they splice those together using these models in mathematics to have them come together smoothly. So you don't always have to have pure exponential data. Sometimes you have exponential fused with quadratic. You guys might see this again in your lives, you might never see it again at all. So this is just like the building blocks that you can work off of. But I do want to talk about one more. One more. Lots of things, as we've talked about, are exponential in the world. We looked at finances, chicken laying, the eggs of chickens. Last week it was dice, probabilities we're getting into. There's so much. Your life insurance, or your health insurance, or your car insurance is all tied back to these exponential models. And they're fantastic. But they're not everything. They're not everything. And here's what I want to talk about. And in order to do this, I need to assign you each a number. So here's what we're going to do. I'm going to walk around the room and give each of you guys a number. Remember what it is, okay? All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. I think I got everybody. 29. Write down your number. What we're going to do, right? You guys got it? I went in a nice logical order. I hope you followed that. I know I did. So what I'm going to do is I'm going to try to force exponential behavior into